We're going to start off looking at number 59, and it's just kind of continuous conversation in regards to solubility, but we're looking at pH as a factor. So it says calculate the solubility of manganese hydroxide in grams per liter when it's buffered to a certain pH. In the first example, it's at 7. So never hurts to set up looking at the equation and seeing how this breaks apart. All right. I do have to look up in the back of the book and see what the KSP value for manganese hydroxide is. There it is. It's relatively, actually, it's quite low. So now I'm going to put this into an equation. Again, I can kind of ignore the solid. And so it's just going to be this and this raised to the second value. So I can say KSP is equal to 1.6 times 10 to the negative 13 is equal to the manganese concentration, which I don't know. But what I do know is the pH. The pH is 7, so therefore I know hydroxide ion concentration, and it's very specific. So this is one of a really good example of how we can ignore this 2. We're not. That's why we ignore the 2. So if I take a look and say, okay, well, if the pH is 7, some really quick work, I can say it's 1 times 10 to the 7. If I don't actually know how to do that, I can raise it to the negative 7, right? And if I do that, I get this value, excuse that, and therefore of course I square the value because that's what you do for the expression, equilibrium. And I'm putting this through, and if I go ahead and just solve the rest of the math, I would get an answer of, for x I'm solving for, would be equal to 16 moles per liter. 16 moles per liter. So wow, that's fairly large. If that's 16 moles per liter, I actually want the manganese hydroxide. Well, it's also equal to 16, I'm going to write it this way now, moles per liter for manganese hydroxide. And I'm almost done. I want actually the grams. What's the solubility in grams per liter? If I multiply times 88.95 grams per 1 mole, and therefore the answer is 1.4 times 10 to the third grams manganese hydroxide. Something that you should be aware of is how I'm kind of going through here is I am showing all those steps in here, the stoichiometry and the dimensional analysis of how, more the dimensional analysis, how I'm actually getting to this answer. And again, this is the amounts per liter, All right, let's do the same problem here. I'm going to shortcut a little bit on this one. For the pH in this one, it's, what do I have? 9.5. So remember 14 minus 9.5. I want the pOH, and that's going to be 4.5. So I'm going to do 10 raised to the negative 4.5. And now I know hydroxide ion concentration. So KSP is going to be equal to 1.6 times 10 to the negative 13, giving me the manganese concentration times, I'm going to use brackets, 3.16 times 10 to the negative 5 squared. Where did that come from? It came from here. And therefore, if that is the answer when I do the math, it's going to give me an answer for manganese. And I will also make the assumption that that is, I'm going to write this down as such. The manganese concentration is equal to 1.6 times 10 to the negative 4, so quite a bit different, moles per liter. I'm going to make the understanding that's also the manganese hydroxide. It's a 1-to-1 relationship. Times roughly 89, not moles, grams per mole. And that'll give me an answer of 1.4 times 10 to negative 2 grams of manganese hydroxide per liter. All right, we got one more in this mix. This time it's 11.8, so what I would have for my POH, or OH concentration, raised to 2.2. So same setup here. This value comes from doing the math from over here. And then the manganese concentration, 4.02 times 10 to the negative 9 moles per liter times 89 grams per mole. That's the molar mass again, which gives me 3.58 times 10 to the negative 7 mole. Trying to figure which words I want to use. Grams is what I want to say. Grams of manganese hydroxide per liter. So this is interesting. When you look at these numbers, it gets smaller each time. The number of grams gets smaller. Here we go. I started off with 1.4 times 10 to the third, and then it gets smaller to negative second to negative seventh. And the reason for that is as the OH concentration goes up, looking at this, start off with small, bigger, bigger. As that goes up, it's like with Chatelier's principle. It inhibits this from going into solution. Okay, that problem is done. Let's go back over to our notes. And this is going to tie in a little bit to what we were just doing on that previous problem. It is the effect of acid on solubility. So this is kind of like another extra problem here. Which of these substances are more soluble in acidic solution than in basic solution? So don't just kind of follow along, have a thought, pause the video, whatever you like, to come up with an answer. So the first one is nickel hydroxide. What do you think? Is it more soluble in an acidic solution or a basic solution? If you said acidic, then you are correct. Why is because the acidic hydrogens will react with the OHs and dissolve it, putting it into solution. Next one, calcium carbonate. If you said acidic, you are correct again, because again, the hydrogens react with the carbonate. C, barium fluoride. Now this might start getting a little more tricky when you're looking at this. Like, I don't know. But if you said acidic, and is like, I was guess, maybe I knew, and it is because of the fluoride. Fluoride is the conjugate base of a weak acid, meaning it doesn't dissolve very well, does not go into solution very well, or dissociate, I should say, and it will react with a hydrogen. All right, last one, D, silver chloride. So that's a solid in there. Roll that around for a second. If you said neither, you are correct. And that is because the chloride is relatively non-reactive because it itself is the conjugate base of a strong acid. And it's not going to react well. And silver simply does not react with OH. Silver pretty much only reacts with chlorides, halogens, and that's mostly it. So anyways, that is the end of this lecture, and I think we're going to have one more lecture after this. I think that'll finish things up.